All right. We can go to the first slide, please. All right, my name's Alan Ho. I am a product manager at Google. And today I'm going to talk about some open source that we recently released over the summer. So I'm going to talk about software for noisy intermediate scale quantum computers. And this is a term that has been come up by John Preskill, talking about quantum computers that are in the range of 100 to 1,000 qubits, and they don't have an infinite gate depth. They have like a certain amount of fidelity in them, so they can only operate for a certain period of time. And so where are we at? Like the question, one of the very big questions that we have in our field is there an impactful algorithm for these noisy intermediate scale quantum processors? We really don't know. And if you think about it, like what's been going on in the quantum computing community, we've gone from systems that have a 90% gate fidelity. That means you run 10 operations and then likely one of them will fail. That kind of quantum computer, you can pretty much write on a piece of paper. And then once you have around 99 fidelity, so you're talking about 100 gate operations, this is when it's useful to record it down, but you could still eyeball what the circuit would be. At 99.9, this is actually the interesting part because it's on the realm of what you can't simulate on a classical computer, but you still really need to focus on the modularity of the system. You need to focus on the number of gates that you're using to operate on. And then at 99.9, there's more complexity, and that when you have logical qubits, that's when you really have to start thinking about super high-level languages and operating systems. So we are really at the 99, we're somewhere between the 99 and 99.9 kind of world. So the first question is, let's take a look at this circuit. Is this a good quantum circuit? And the way to read it is, I'm doing a Control-Z operation on A and B, then followed by a control operation on B to C, then control operation on C and D, and so forth. It's a good circuit? Yes, terrible. It's actually not good, because if you're doing it in a serial fashion, then you're going to have a large depth. Well, is this a good quantum circuit? So it's a little bit more. It's a little bit smart here, right? So you're kind of lowering the number of gates, but no, because in a quantum processor, specifically the processor that we're building right now, which is on a 2D lattice, this kind of application doesn't take into account the constraints, the spatial locality constraint. Is this a good circuit? Right? It's now a little smarter. It's thinking about it's thinking about the 2D grid. Let's try eyeball it. Maybe. So it turns out it depends on what kind of quantum computer you're actually running it on. And what I'm showing you here is that if you're running it on, let's say the B, if you're doing a gate operation on the A and B qubit, you can't do it on the D and E qubit at the same time. And the reason why is because for the Bristlecone, our quantum processor that we're building, what we're doing is effectively tuning the qubits to be at the same resonant frequencies. So you don't want to have adjacent qubits doing these 2 qubit gate operations. So it really depends on the architecture. So our thesis is that when you're developing your NISQ algorithms, you got to be very careful about the attentions of hardware. And so it actually makes sense that the tools for NISQ algorithms should aid in telling you about those details. And so our solution is Cirq. It's on GitHub. And by the way, I want to do a shout out to some of the startups like Zapata Computing, CQC, and QC Ware, companies, NASA, for helping us prototype and be part of our alpha release. And you can just download on GitHub. And the way we're thinking about Cirq is that it lies in the intersection of hardware, software, and exploring NISQ algorithms. It's an open source Python framework. So the reason why we chose Python is because a lot of physicists know how to use Python. and it's geared towards writing and optimizing and running your quantum applications. So actually, for those who have laptops, it's actually a good time to bring it out right now. So you're going to be able to follow some of the exercises. I'm going to give you a few seconds to look at this. And I'm going to come back to this, by the way, in a little bit if you need a little bit more time. Yeah, just take a picture. That's actually the best way. So I just want to kind of give you some internals of how Cirq works. Basically, the user creates some code, and then there's actually two sets of operations. There's a circuit phase and there's a schedule phase. And basically, at each of these phases, you can optimize them. And let me kind of give you some information about what's the difference between a circuit and schedule. So a circuit, what we do is we discretize the operations into groups called moments. So these are gate operations that happen at the same time. It ignores how long these gate operations take, and it's fairly easy to manipulate. And schedules, what it is, it's basically continuous. This allows you to actually, our Permion framework allows you to tell you when a gate operation begins and gate operation ends. And so because these gate operations are all slightly different, for example, the 1-qubit gates are much faster than 2-qubit gates, giving you this ability to kind of like, at a very low level, tweak the timing can be very useful for the system. The other thing that makes it different is that we actually want the hardware abstraction to be exposed by the programming language. So we don't have any mechanisms within Cirq to just generically allocate a qubit. You got to pick and choose the qubit you want to use. And the reason why this is very important is because in these early NISQ devices, even in a system like this, not all qubits are going to be equal. Every qubit will have slightly different coherence times, and every qubit to qubit interaction will also likely be different too. And so that's why we want to give the developer the ability to choose which qubit they use. All right, I talked about the device constraints. So what we can do here is that when you insert gate operations, it will automatically take into account the constraints of the device. So for example, what I'm doing here is between qubit 0 and 1, I insert a control Z. And if I insert another control Z at an adjacent qubit, using this insert strategy, earliest, it will automatically try to schedule as early as possible, but it won't violate the constraints. So this kind of takes care of the problems for you. And the other big question that we have is, what are the good algorithms for classical co-processing? We actually don't know what it looks like. We don't know if the classical computer should sit beside it. We don't understand what kind of capability, what kind of operations you need, feedback, et cetera. So one of the things that we want to do with Cirq is be able to provide a framework for you to answer these questions. So there's very minor, small things that we're doing in Cirq right now today. For example, the simulator itself, it's not running in the cloud. The simulator actually runs on your laptop. And what that allows you to do is that you can build your classical quantum algorithms, and it will execute, you can use regular Python for executing your classical algorithm, and then call out to Cirq that's also running locally on your laptop. So you have this fast feedback time, and you're able to explore your algorithms much more easily. Whereas if the simulator was in the cloud, it'd be a pain in the butt because you have to always be, from your laptop, be doing these remote executions over and over again. Another thing that we have in the framework is this thing called parameterized sweeps. So this is actually more of a function of the computer that we are building. What this allows you to do is basically create variables and then sweep over a period of those variables. So for example, in this example, we have two variables, A and B, and you can see that there's control Z's operations that are parameterized by A and B, and then we can sweep over that space. So it's from for A, it's going from 0 to 1 at a 0.1 increment, and then from B, it's going from 0 to 1 at 0.1 increments, which gives you like 100 different measurements. So you can basically sweep over these things. And this is actually very useful in the variational algorithms. So for example, if you recall earlier today, it talked about taking a gradient and having to explore the energy landscape. By using these sweeping capabilities, it allows you to like tune the parameters and get a whole bunch of results of the energies in that particular location so that you can take gradients easily. Talking about our simulators, it's built in with a NumPy simulator, so it supports multi-threading, et cetera. And at some point, we're still working on more simulators, and the idea is that the simulators could also live in the cloud too. So if you need to do very large simulations above 20 qubits, you can actually do it in the future when we release a cloud service, it will have that available for you. And so Cirq is going to, idea is that if you use Cirq to program it, this is going to be there's going to be compatible with our quantum processor that we're building out as well. One other point too is that we kind of dog food our own framework. So one of the frameworks that we built, very high level frameworks, is OpenFermion. And OpenFermion is a quantum chemistry package. It's compatible with multiple languages, Project Q, QuizKit, even Q#. And what we wanted to do is that we want to actually make it easy so that you can go from a molecule, like a molecule geometry, compile it down, compute the basis sets, get the Hamiltonian, figure out map it to qubits, and then map it to actual hardware, and then be able to execute on the chip. And what we've done is that we've also, you can just only, and this is basically doable in just several lines of code. So you can see where kind of the OpenFermion on the right is where OpenFermion begins. You're calculating you're setting the geometry, you're calculating the Hamiltonians, and you're printing out the qubit operators. And then on the on the left side, you're showing that once you have your qubit operators, you can compile those qubit operators into a circuit and then put it and run it on Cirq. So Cirq is open source. It's Apache 2. It's very alpha. We're very open to contributions and collaborations. In terms of what's kind of the next thing that we really care about is having really good noise models. We also would love different hardware backends. So we're working with the university right now to try out actually implementing a simulator for ion traps. And this becomes very interesting because if you could use one platform to try out your algorithms on ion traps versus superconducting qubits, you can kind of get a sense of the advantages and disadvantages of each. So for example, ion traps have much better connectivity, whereas maybe superconducting qubits has much more faster execution time. And we have a user group too. And here are the main engineers for our group. And I kind of like to lead with an example. So I'm going to go into the demo side of this portion. All right, so if anybody has this, if anybody wants to follow this, they can just type in the Google URL that we did earlier. So it's fairly easy. It uses, you use pip install to install the package. So then I'm printing out one of the devices that we have. So this is a device called Foxtail. This is a device we haven't released to the public. It's a 22 qubit device, basically two lines connected together. And this is kind of like what a circuit looks like. You basically you create your qubits, and then you create an array of operations, and you basically add that array to your circuit. So this is talking about the insert strategy. So we have multiple ways that you can insert your qubits. We have multiple strategies for insertion. So for example, over here, we talk about insert strategy earliest. So it tries to, when it appends these, so what it's doing is that it's first appending a control Z gate, and then it's appending two Hadamard gates, and it's trying to do it as early as possible. So it's putting it as close as possible to the first gate. However, if you use a different strategy, for example, insert new, what this is doing is, versus insert earliest, what's doing is that it's creating a new moment for every gate that you're inserting. So as you can see here, the gates are getting longer. All right. So I have some exercises here for you to create a circuit. I'm looking at time. I want to like get people out of here earlier rather than later, so I'm going to skip this. But then the other thing is that I just want to show you how you can also, so I'm going to create a circuit, and I'll show you a little bit about the simulator. And if you run, so for example, the simulator, you can run it, and because it's probabilistic, you're getting different answers. But one of the other things that we have too is we also allow you to simulate the entire wave function. So we have basically this basically is the actual wave function. It allows you to get out the entire wave function. And this is useful for exploring various quantum algorithms. All right. And then we have kind of features that allow you, we have kind of helper functions that allow you to create histograms, things of that sort. And in terms of gates, we have a plethora of gates. So we have the very common gate operations that allow you to do, that people use. But we also have features that allow you to create your own custom gates as well. So in the bottom, if there's more exercises below, it actually shows you how to create those gates. And yeah, the RX, RY, RZ gates are probably the most useful for those who actually, do quantum programming. And basically, you can use these to plot various grids. And so actually, I suspect that a lot of people here are not quantum folks, so I want to kind of like motivate, I want to write a small application for everyone to kind of give them a sense of how to write a quantum application and the power of quantum computing here. So one of the examples, you may have heard about Deutsche, the David Deutsche's algorithm. One of the examples in power of quantum computing is being able to discover things in a black box, right? So what it is, it's you are told something about f of x's structure, and you want to derive f of x. Now you might say, like, when is this kind of, what's the use of this? One thing that you've seen quite a bit is neural networks. So you're promised layers, connectivity, activation functions, et cetera, and you want to derive weights for each connection. Now, I'm not going to do this because this is I'm not saying that we can use a near-term quantum computer to train a neural network. But what I'm going to show you is something simpler. This is called the Bernstein-Vazirani problem. And basically what it's saying is that you have A, which you don't know, dot X, which is your input, plus B. And if you actually, what you're promised is like A0 times X0. So A can be between 0 and 1. And you basically want to discover what A is, right? And you want to derive what A is. Well, classically, to kind of, if you don't know what A is and you have this black box, you would need to query the system n times. You would have to query it n times. Whereas in quantum, you can query it just one time. So I'm going to be a little bit hand-wavy with the algorithms here to make it a little bit more understandable. And the way that you would kind of do this is that you would set up a quantum circuit. You would take this black box and then perform an operation on it. So you get this unitary operation, this -1 to the power of A plus dot X. And then you would have a circuit that would be the input. You would prepare a state. You would prepare an input state into the black box, and then also prepare some circuits on the outside of the unitary to get the actual answer. And to kind of give you maybe some intuition of what you're doing is that this first few layers of gates, it's basically putting your qubits in superposition. So it's exploring all the ones and zeros at the same time. And when you execute, after you execute the operation, you do this, you do a set of Hadamards, and then basically you derive A. So how you actually implement this on Cirq? So I'm gonna, what I'm gonna show you here. So this is the oracle. So it's basically, this is taking in the input qubits, the number of input qubits, number of output qubits. This is the 0000 and then that 1 at the very bottom. And then also telling, and then you're trying to just set up what the oracle, sorry, let me just blow this up so that we can see this. What you're trying to do is you're trying to set this up. So you can code this up. And if people are working on the exercise right now, I have this example function already kind of set up here. So it makes an oracle, and you create a circuit. And so you have to add some code to before the oracle, and then you add some code, you append the oracle, and then you add some code after the oracle, and then you do your measurement. So is anybody following the exercise right now? Okay, if not, I'm just going to go straight to the solution then. All right, so what we're doing, just to recall, we need to set a majority of our input qubits. We need to put a Hadamard on each of these. And then we need to take this one state and then put a Hadamard in it, right? So let's kind of go back, see what we're doing here. So we're putting, So we're putting a Hadamard on each of the, this is the first, actually, unfortunately I did it the opposite way. We're putting Hadamards on all of the input qubits, right? And this qubit, this is in a 1 state, right? So how do we get a 1? So initially the system is initialized in 0. How do we get a 1? We flip it around on the x-axis. We do an x rotation. We flip it around 180 degrees. So that corresponds to this x operation. And then you add on this the Hadamard operation, right? And then to measure, you just put a Hadamard on each of the qubits, and then you measure the results. So let's try this out. Okay. All right. So as you can see here, we put Hadamards on all these input qubits. And on the output qubit, we had an X, which takes it from a 0 state to a 1 state and adds a Hadamard. This is the oracle. And then these are the Hadamards that were added on the qubits that you want to read out. And so theoretically, if you read out the values, this should correspond to this to the A matrix 1 1 1 0 1 0 1 0. So we look at the results. Unfortunately, it doesn't read very well. What it's saying is that I've executed it 3 times. This is the first qubit. This is second qubit, third qubit, fourth qubit, and what you'll see is that it just so happened that when I executed, all the results are identical. And it turns out that this just matches the A. So that kind of gives you an idea of how you would program this application. All right, so that's actually the end of my talk, so thank you. So we have time for questions. All right, any questions about Cirq, our roadmap, things of that sort?
All right. So about the example problems. So if you have multiple solutions for A, how can you, how those the quantum circuit to find the only one solutions where the
So in a quantum computer, what you want to do is you want to sample it, you want to execute it multiple times, and you want to pick the most common answer. Yeah, so that's what you would do. Any other questions? Sorry, we have a question over here. Oh, okay, we have one here first.
Well, I have a question. So you mentioned the Foxtail processor, which had 22 qubits, I believe. The Grover required 8, but all your examples were on a simulator. Is it possible to do a Foxtail computation via this example?
Sorry, so say that one more time.
All your examples use simulators. I was wondering if it's possible to use your actual processor because it only took 8 qubits.
Oh, no, so the Foxtail machine is a test device that we use. So it doesn't, it's one of the generations that we've built in the past. It's not hooked up. So our Cirq simulator does not talk to the Foxtail. Our Cirq system does not talk to Foxtail right now.
Okay, thank you.
Yeah. So we had a question over here.
I was curious about, also curious about the Foxtail machine, but particularly the choice to make the grid 2 by 11. What's the benefit of having a long, narrow layout?
Okay, yeah, actually the best, if you're kind of interested where we were going, this is actually, it's a little hard to describe. Just give me 1 second here. I can show it to you. Give me a second here. Sorry, would you be able to show the slide? Okay, yeah, so probably the biggest announcement that we had was that we've created a chip called bristlecone, which has all the, basically is a 72 qubit chip on a planar lattice. And so what happened was, kind of like the innovation there was that we separated the qubit layers from all the wires. And just before this generation, we had just it on 2 lines. And the reason why is because we weren't able to get all the wires, all the resonators and wires within this small little lattice. And so it was actually a generation back to do some testing to see whether or not that architecture would work. So that's why it's an interim version, but this is where we're really, this is what we are building this is the processor that we want to do our quantum supremacy experiment, which Scott Aronson will talk a little bit more about on day 3.
Some of the other speakers talked about hybrid classical quantum algorithms. Are there any features in Cirq that might help you do that?
Yeah, that's something we're building out right now. There's some things that we have, for example, the parameter sweeps, being able to search a smaller space, being able to search a space of parameters. And that's really good because what you can do is that instead of making a call to your quantum processor and getting back information, you could actually send you can send a parameter sweep to your quantum processor, and you can do a little small sweep of the energy landscape, and then get it back. So that's one feature that we have in. But we are actually building a lot of other features. And actually, one thing I would like to tell you about is that I think the entire industry is banking on these variational quantum eigensolvers. And although they're very, very powerful, it has this outer loop optimization, which is very, very difficult. And I'll talk a little bit more about that tomorrow, but we want to build more features around that outer loop optimization to make it easier for these hybrid classical quantum algorithms.
Hello. Earlier, you talked about the simulators, and the slide was saying that it was multi-threaded and allowing multi-processing. So I guess my question is, so you're saying that you already have a simulator that can work on a distributed architecture, basically, and get the most out of a cluster, for example?
So for the simulator that's right now in Cirq itself, it's designed to run on your laptop. So it's not the most high performance simulator. It's written in NumPy, which is not the most highly performant simulator. We do have simulators that do run on a distributed system, like a massive scale distributed system. But those are actually very clunky to work with, and they're not very easy for exploring algorithms. So when we release a cloud service, we will probably have a distributed simulator at some point. But for right now, for Cirq, it's designed for your laptop.
Okay, so maybe a next simpler suggestion would be, are you guys planning to make it more compatible, for example, with accelerators such as GPUs or FPGAs that could be on my laptop?
So one group that you may want to talk to is NASA. So they have some very interesting, they've actually released a really interesting paper on simulating of quantum systems, of quantum computers that I'll talk a little about tomorrow. And those things lend itself very well to acceleration on GPUs, and something we're actively looking at. As of now, internally within Google, we try to max out a lot of the scientific instruction codes on these Intel processors as much as possible. The other issue is that a lot of these, like tensor processing units, et cetera, they're very low precision, they're low positioned, and for a lot of the quantum simulations, that's not what you want. You want at least 32 bits of precision. Any other questions? All right, thank you very much.